now thank you for recording that. Is a CNRS permanent researcher in Nice, France, which is springtime now. I bet it's very beautiful and sunny. And her research centers around binary systems and their behavior. That's one of the reasons why I invited her. I want to hear all about her research, just for me. And last year, her research focused on what gravitational wave detection tell us about evolution of massive stars. And she's a member of LIGO-Virgo COGRA collaboration, as well as the LISA consortium. And thank you very much. I'll give you the floor. Thank you.
Thank you, Petra. Thank you for inviting me. Well, good evening, everyone. It's weird. I still feel I just woke up. I'm going to give an introduction on what we can tell with gravitational waves. Petra, maybe you know most of this, so we can also discuss more later. I guess you can see my screen now?
Yes.
Okay, so I can't see any chat or anything anymore. So I believe I have about an hour. So my plan was to be very open for questions during the talk. So if anyone has a question, I guess you can raise your hand or put it in the chat. And Petra, you're free to interrupt me anytime and say someone has a question. That's completely fine by me.
Okay.
For a remote talk, I think it's important that we can still keep some connection.
Sounds great.
So anyway, so I work on gravitational waves. I actually didn't train in gravitational waves, so I had to learn all of this from the beginning, and so that's what I will also do here. So very basically, how do we actually create gravitational waves? So if you look on Wikipedia, you find that a gravitational wave is a propagation of a disturbance of space-time. And as you can see here, you have a binary that is creating these ripples, and that's really an easy way to represent gravitational waves. The thing is, to make measurable gravitational waves, you actually need to be moving massive objects at speeds that are close to the speed of light. So if we think about massive objects and speed of light, we're really thinking about extreme objects and extreme phenomena like compact objects such as neutron stars or black holes or explosions of stars. We're really thinking in that regime of really massive and extreme things. The other ingredient we have is that to make gravitational waves, you need something with a quadrupole moment. So it's something that is not spherically symmetric. And so a binary where you're just rotating around each other actually fulfills this requirement. And so this is why binaries made of black holes of any masses or neutron stars or white dwarfs or possibly other things are the places where we are looking for gravitational wave emission. And gravitational waves, in the same way as electromagnetic waves, actually come over a whole range of frequency. At the moment, we only have the LIGO, Virgo, and COGRA detectors that are operational. And so these are in the kilohertz frequency, so they're on the complete right on this plot. So what I'm showing here is the spectrum of gravitational waves that we expect as a function of frequency. On the x-axis and the y-axis is the actual gravitational wave strain, little h, that I'm showing in the formula. And so at the highest frequency, you have to keep in mind that the gravitational wave frequency is twice the orbital frequency of a binary. So if you have kilohertz gravitational waves, it means you're talking about objects that rotate around each other 1,000 times per second. So just imagine two black holes turning around each other 1,000 times per second. That's really what we're talking about. And it's really an extreme thing. And obviously at this speeds, at this type of periods, you're really about to merge. And so the things we see with LIGO, Virgo, and COGRA are merging objects. In this frequency band, we also expect to see signatures from the collapse of massive stars in supernova. I'll very briefly mention that at the end of my talk. And possibly also the rotation of what we call pulsars. So pulsar is a neutron star, so the remnant of a massive star, that is rotating quickly and is emitting a beam of light that occasionally is centered on the Earth and that we can detect. And so the rotation of these objects can be in the kilohertz regime, and so we expect that someday we could detect these systems if the neutron star is not quite spherical. So if the neutron star has a bit of a bump, a little bit of a mountain, then we could detect that. So we expect actually the size of this mountain to be centimeter size. So it's actually very small, but that should be enough to be detectable. So this is the high frequency regime. But then, so with LIGO Virgo, we see the merger of a binary, but effectively that same binary has just been rotating around each other for billions of years and slowly emitting gravitational waves until actual merger. So you can find the same system at lower frequency, and that means it will also have a lower amplitude, but you can actually detect some of these systems at lower frequency. So in the middle of this plot, I'm showing here the LISA sensitivity curve. This black line is what we expect the future space mission LISA to be able to detect. So that will be gravitational waves in the millihertz regime. So this means that things are turning around each other in a few minutes, a few hours, which is already something that seems much more easy to comprehend for humans. And so at these frequencies, we're going to see the merger of more massive systems. And so this is where we will have supermassive black holes, the ones that live at center of galaxies. They will be merging when they have periods of, let's say, an hour, and they will be detectable by LISA. Now, if you look at the, so this is one thing LISA will see. The other thing that LISA will see, and this is something I work on in Vetra as well, are binaries that are just turning around each other. And so this will be black binaries made of the remnants of stars, so black holes, neutron stars, or white dwarfs. And if you look at the equation that tells you the strain of the gravitational wave, you see that lower frequency means lower strain, lower amplitude. So these things are harder to detect, and it means we'll only detect systems in our neighborhood, in our own Milky Way. So with LISA, we're going to detect these, what we call resolved galactic binaries, which is really individual binaries that are just turning around each other. And then at the very low frequency, what we call the nanohertz, we have systems that turn around each other really in more than a year. And this is the what we can detect with pulsar timing. So it's the idea that we use the Milky Way as a detector. And we are essentially timing the arrival of pulsars, of these pulsars I've actually mentioned before. And we have many of them in the galaxy. We're timing all of them precisely. And when we see a change in the arrival time of the pulses, we can say that a gravitational wave has been coming through. That's the idea. So this is the International Pulsar Timing Array, IPTA, which has a strong component in Australia. And with these, we would see the mergers of the really most massive black holes. So I really don't work on these. I have a few slides on the supermassive black hole mergers, but I don't think I'll get there in an hour. But if you have questions, we can definitely go there. So now, if we look a little bit into what we actually have found with these gravitational wave detectors. So the plot I'm showing here are the masses of neutron stars and black holes that we currently know of. So the masses are shown on the y-axis, and there's really, the x-axis doesn't have any meaning. It's just a pretty representation to show it like this. And what you see is that in yellow, we have neutron stars. So these can either be seen as pulsars, as I've mentioned before, or they can also be detectable when they are accreting from a binary companion. And then you make this type of jet, what I'm showing in red here. And this is essentially what you detect. You detect a jet or a disk around the neutron star rather than a neutron star itself, because it's a very faint object and it's very hard to detect. But we see them in the Milky Way, and they have a mass of around 1.4 solar mass, can go a little higher up. And then in red are the black holes that we know of in our Milky Way or in nearby galaxies. And so the thing is, a black hole, by definition, doesn't really emit light. And so we can only see it when it's interacting with a companion. With electromagnetic lights, we have never seen an isolated black hole. And so we see the black hole because it's accreting from a companion. There's also recent work that is showing that, for example, in the Gaia data, so Gaia is a satellite that very precisely measures the position of stars, they can see that certain stars have a wobbling position, and so they're moving. And so we think that there must be a binary companion to explain why they're moving all the time. But if the companion is not visible, we can conclude that there's a hidden black hole. So there's a few claims. Most of them end up being discarded by later observations, but some of them are still valid. So maybe one of them is really a true hidden black hole. So this was the world we knew before LIGO and Virgo turned on. And that since then, the scenery has changed quite a bit, because with gravitational waves, we actually see all these black holes, the ones in blue. All these blue points are the merger of two black holes. And you see that it is really showing us a completely different picture of the remnants of stars. And so we shouldn't forget here that most of the focus with the current detectors is black holes and neutron stars. But at the lower mass, we have white dwarfs, which are the remnants of stars like the sun, for example. For the moment, they're visible with electromagnetic methods. We can see white dwarfs with telescopes. They're faint, so we don't see them very far away, but we do see them. But eventually, LISA, the space mission, will detect many more of them, up to actually the Magellanic Clouds, so the satellite galaxies from the Milky Way. And so most of what I actually do is trying to understand where these distributions come from, what they can tell us in terms of how stars form and how they evolve. So that's most of what gravitational wave astrophysics is about. So astrophysics means there should be stars involved somewhere. And this is just really to take it back a few steps. I know you all come from different backgrounds, so I felt a little intro on astrophysics was useful. So what I'm showing here is what is called the initial mass function. It's what the distribution of mass of stars at birth. And you see that we have many more stars that have low mass than high mass. So at the moment, the initial mass function is still something we don't fully know, but we know this. There has to be, it's a strong power law, and we strongly prefer low mass stars. So stars that have a mass below 8 or maybe 10 solar mass will turn into a white dwarf. This is this green region. And essentially 95% of the stars will turn into white dwarfs. So people sometimes think that white dwarfs are not interesting, but remember, 95% of stars do make a white dwarf eventually. And then in the pink region, so stars between, let's say, 8 and 20 solar mass will end their life as a neutron star. And then even more massive stars will likely turn into a black hole. That's the blue region, which is actually not even shown on the plot. And this is just to make you realize that black holes come from actually really rare stars. Only about 1 star in 10,000 at birth is massive enough to eventually turn into a black hole. So when people think about what they can do with black holes, you're really thinking about the most extreme stars and rather rare stars. And so we can look a little bit into how stars evolve. In general, so here on the x-axis is just different mascots of the stars. So the one that will turn into white dwarfs, neutron stars, and black holes, and you can see time evolving from top to bottom. It's a very simplified picture. But in general, as stars are, so the most important thing is to remember that the key parameter that explains how stars evolve is their mass. Essentially, if you know the mass of a star and a little bit about its chemical composition, you should be able to predict how it's going to live. And the more massive, the faster the shorter their life, the faster they evolve. So a star like the sun will spend about 10 billion years turning hydrogen into its core and turn it into helium. Then for a while, after that is gone, the star will start expanding and become what is called a red giant. And it will burn this helium in the core into carbon. Oh, sorry. Sorry, someone was calling. Sorry. So, no, I lost my train of thought. So the helium then will be turned to carbon and oxygen. And at that point, the star is has expelled quite a lot of its atmosphere into a planetary nebula. And the star is not massive enough to get warm enough into the core and to burn the carbon and oxygen and anything else. So the core of the star will just cool down, become a white dwarf. And whatever was outside will be a beautiful planetary nebula that you can see with many telescopes. And so that's the life of a low mass star. More massive stars have the same evolution, but on a much faster time scale. And they will, once they've burned helium into carbon and oxygen, they will keep on burning things because they're massive enough. So it's warm enough in the core for nuclear reactions to keep on going until eventually the star is making iron. And the problem is that iron is very stable from a nuclear physics perspective, and it's actually impossible to burn it into something else without adding a lot of energy. And so at that point, the star cannot sustain its nuclear reactions, and it's going to collapse and have a supernova explosion, which can lead to the formation of a neutron star or black hole, depending on the mass. So this is a very simple picture for a single star. But massive stars are very important because really they shape a lot of our universe. If you look at a picture of a galaxy, all these red points are actually the areas around massive stars. Mostly when we look at faraway galaxies, if they're young, we see the massive stars. And because they're so luminous, they can be 10,000 times more luminous than the sun. And they make these impressive winds. This is Eta Carinae, which is an evolved star. And you see these blobs of material, which is material that is expelled in stellar winds that can be sometimes very eruptive. So in short amount of time, a lot of material can be expelled. And so this material obviously goes back to the surrounding medium and can then have a lot of impact in terms of chemistry, but also it disturbs the medium, so it changes how stars form. And so really, massive stars have a huge impact on their surroundings. But once they are done with their life, which takes about somewhere between 1 million and 10 million years, so it's very short, they turn into these black holes or neutron stars, which are essentially invisible unless we have a gravitational wave detector. And so these compact objects are really interesting from a physics perspective, because these are places where general relativity dominates, where we can do interesting nuclear physics. We can study relativistic outflows where we can emit X-rays and gamma rays. And so these are beautiful places to do interesting physics. So massive stars are important for the way the universe evolves, but also because they're the progenitors of these very interesting compact objects. So how do we actually get compact objects to merge? The problem is that the time to the merger scales as the separation of the binary to the fourth power. So that means if for some reason your stars have evolved slightly differently and they're only just 2 times further apart, their merger time will be more than 10 times larger, and they might actually never merge. Most of the compact binaries are actually not predicted to ever merge in the Hubble time because they're too far away. They just keep turning around each other without nothing happening. Now, if you take 2 massive stars, their initial distance, the shortest distance they can have is the size of the stars, is set by the radii of the stars. Because if they would be touching, they would merge as stars and you would never have a black hole merger. So they can only be this close. And if you take this distance of just 2 stellar radii, you take that distance, you replace each star by a black hole, you're already too far apart to ever merge. And so that's really the basic problem of why do black hole mergers even exist, because very naively we wouldn't expect. Well, the good thing is that most massive stars form in pairs or actually triples or in clusters. And so there will be many interactions that will actually lead the compact objects that they form to be actually close enough. So this is an artist's impression of 2 massive stars that are interacting and they're sharing an envelope, which is why it looks like a peanut. This is an artist's view, but it's based on observations with high angular resolution that actually show that these type of stars exist. So many stars are in binaries, so we can expect all these interactions to lead to mergers. The other thing we know is that there are many stars that form in clusters. And in clusters, you have millions of stars in a few parsec. And so you have many n-body interactions that will eventually lead the stars and their compact objects to merge. And so these are sort of the 2 main pathways that we expect for for the compact object mergers that we see now. We think that binary black hole mergers come from any of these things. And so why it's interesting is that with these gravitational waves, we can actually learn things about how the stars evolve. Either single star evolution or the combined evolution of more than one star. So how do we actually do this? In a binary, the first thing you have to do is to make two massive stars of at least 20 times the solar mass. And as we've seen in the beginning, massive stars are rare, so these things don't happen that often. But let's say we've succeeded. The problem with massive stars is that, as I said, they are rare, but they're often formed in binaries. But their first problem is that they make winds. So this is again this image of Eta Carinae, and this outflow is mass that is being lost by the star. And if that mass is being lost by the star, it might actually prevent the star from ever making a black hole. So why does this happen? The thing is, we have the core of the star, and in a massive star, that core is really warm because of the mass. And if you remember just basic the black body physics, the warmer you are, the more intense the radiation that you emit, the more energetic the radiation you emit. And so massive stars emit a lot of UV. And now, if you have the atmosphere of the massive star, that atmosphere is going to be subject to the UV radiation that is coming from the core. And so now if you have a star that is made of mostly hydrogen and helium, so in astronomy, we say that it's a metal poor star because anything that is more massive than helium, we tend to call a metal. So if you have a star with only a few metals, the cross-section between these UV photons and these metals is quite small. So that means that the stellar wind, the outflow that you will make is quite small because it's hard for the photons to push the atmosphere out because the interaction is just not really efficient. Now, if you have a chemically much more complex star, what happens is that the cross-section between, let's say, an iron atom and a UV photon is actually very high. And so what happens is that these UV photons will hit the atmosphere and efficiently push it away and have a strong wind. And as a result is that stars with few metals make rather big black holes, and stars with a lot of metals make tiny black holes, or not even black holes. And so our sun is already at the stage where it's considered enriched in metal. So the stars that make the massive black holes that LIGO and Virgo often observe come probably from these low metallicity stars. So this is one thing to keep in mind, is that the chemical composition of the star actually matters. So this was the first problem into making black hole binaries, is the fact that we have stellar winds. We have a second problem, is that massive stars exploding with supernovae. So supernovae are at least the most luminous things we see with electromagnetic light. We can actually, a supernova can outshine the total flux of a galaxy. This is just an example of a supernova that was found about 10 years ago, actually, by an undergraduate student who were doing a research project on this galaxy. And you suddenly see it start appearing. And it's called a supernova. It's a nova because it appears suddenly, and supernova because it's big. And it's related to the collapse of a massive star. And the problem is that you have a binary. You suddenly have a collapse of one of the objects. So it's going to lose a lot of mass. So just from a perspective of conservation of momentum, if you lose a lot of mass all of a sudden, the orbit of your binary is going to change. Also, the explosion mechanism of a supernova is probably not symmetrical. And so these two things combined mean that the black hole or the neutron star that you have formed when your supernova exploded is going to receive a kick. And if you have your binary, one of the objects gets a kick, it might very well break your binary. And if you break your binary, well, you're never going to get a merger. So this is one of the main things that stops the formation of compact object mergers. It's a quite uncertain process, and it's sort of one of the knobs we tweak when we're trying to adjust models to the observations we have. But okay, let's assume we have survived the supernova stage. Then we have this X-ray binary stage that I mentioned before, where the compact object is accreting from the companion. And so this accretion probably makes a disk, and also jet. And so mass is being transferred from the companion that is still a regular star onto the compact object, either through winds or rush lobe overflow, which I'll talk about later. And so this mass transfer is going to change the masses of the two objects. It's going to possibly, if you change the masses, you also change the dynamics. Just by Kepler's law, if you change the mass of your object, your orbits are going to change. And so mass transfer is an important ingredient on how stars evolve, how binaries evolve. So there's this notion of rush lobe overflow. So the rush lobe is a mathematical definition that is the boundary between the gravitational influence of two objects. So you see here in this object, you have M1, in this drawing, you have M1 and M2, and in the middle, you have this L1 point, and at the intersection of these two teardrops, that is really the crossing point from matter that would go from one object to the other. So if a star fills its rush lobe, so it's overflowing this boundary, this thick line, matter that was belonging to one star can now flow onto the other one and lose mass. And this is what we call rush lobe overflow mass transfer. This can go on for a while. It's a stable process. It's rather gentle. And it stops when the stars get back into their rush lobe, either because the star is shrinking, and then it comes nicely back into its rush lobe, or because the rush lobe is getting bigger. And so this can happen because the rush lobe, the size of the rush lobe is proportional to the separation of the binary. So if your mass transfer results in a widening of the orbit, suddenly your star can find itself back in its rush lobe, and the mass transfer stops, and everything is all back to normal. However, if you're transferring mass and your star cannot really adjust to the mass transfer because it changes its structure, it is often the case that your star will get even bigger. And so as the mass transfer is happening, the star gets even bigger, the mass transfer gets even bigger, and this is a runaway process, then we have what we call a common envelope process, which is unstable mass transfer, which happen on much smaller timescales. And so this common envelope phase is likely a crucial ingredient in how binary compact objects get to merge. So I'm showing a cartoon picture here on the top right, where you have your compact object in blue, and then the companion star has an expanded envelope because it's become a giant, and the compact object really lives inside this envelope. And because it's living inside of this envelope, there's a lot of friction. And this friction will bring the compact object much closer to the other star. And there will be an exchange of energy between the orbital energy of the system and the envelope. And that means that, this means that eventually the stars may get close enough and expel the envelope. And if the envelope is gone, both stars get back to being small, the common envelope stops. However, if for some reason this process doesn't work, the energy can't really be changed from the orbit to the atmosphere, then this process doesn't stop and the stars just merge. And that means they will actually never make a binary black hole merge. So I'm going to show you a little well, it's not a cartoon, it's actually a movie from hydro simulations. So we're going to look at a common envelope phase of two low mass stars. So on the left, we're seeing them from above the plane of the orbit. You see the two green points. So the giant star is, well, obviously the biggest one, and you see the companion is the tiny green dot on the right. And then on the other picture, we see it, but seen from the side, and you see the evolution. Very quickly, the orbit shrinks. A lot of material is being expelled, and the two objects get much closer to each other now. So this is a simulation for a low mass binary. It's actually really hard to simulate these objects, and for massive stars, we're still struggling with it. Also, it's very hard to observe these things because they're short-lived. So we don't have many massive stars, and this phase is short-lived. So if you combine these two problems, it means that we don't really get to observe these phases. So we don't really know how the common envelope phase works, but we know it must exist. And so it's one of the main ingredients that we have to make compact object mergers, but it's also a main uncertainty in what we do. In any models we have, it's a phase where we do our best, but effectively we're probably still far away from what it should be. So, okay, let's assume we survive this common envelope phase. Our second object is also going to turn into a black hole or neutron star. And so we have a second supernova, which can also break the binary, although this is much more unlikely just because the orbit is already much tighter. So breaking the binary is often much harder. But let's assume we've survived this, and then we have two black holes, and they will just in spiral for billions of years and then merge. So it's really all about shrinking this binary. And just keep in mind that if you have two objects, you want to get them closer together, you need to lose angular momentum. So one way is to lose mass. So winds will do that. If you have two massive stars, they will likely make winds, and so that will make your binary wider. So that is not helping you. If you have mass that is being transferred in a gentle way, basically mass is leaving one star and just going to the other, the binary is shrinking if you transfer mass from the most massive to the least massive. But actually, stellar evolution is such that you can also transfer mass from the lower mass to the more massive companion. In that case, your binary will expand. So that's not helping. Now, most cases, we actually think that when there is mass transfer, some of the mass is being lost in space, like in this common envelope process. And in that case, we often have very important shrinking. But basically, mass loss of all kinds and winds will be the dominant factors that explain the evolution of stars towards making compact binaries. So I've told you about these different phases. What if effectively you have to keep in mind that these first steps take typically less than 5 million years, which is really short if you remember that the universe is 14 billion years old. And then when we have the compact binary, we're really talking about billions of years of in spiral. So it's very hard to get the first million years right, but they have such a big influence on what's coming next. So keep that in mind, that most of the binaries we see merging may come from stars that were formed quite a long time ago because of this very slow evolution. So I've talked a lot about binaries, but there's another way we expect binary black holes to get to merge is in clusters. So star clusters are these regions where we have somewhere between 1,000 and even 10 million stars in a small radius. And so we can have globular clusters, which are full of old stars. They're quite dense and massive. We can also have young star clusters, which are less dense, much less massive, and they will dissolve much more quickly, but they're quite numerous. Actually, a lot of massive stars form in groups or clusters. And then we also know that at the center of galaxies, we have these nuclear star clusters, which are really dense, really massive. And so all these environments, we will have a lot of in-body interactions that can possibly bring binaries close to each other. So if we look into a little more detail, so in-body interactions are complex and simulating them is hard. But in general, so this is just a cartoon picture of interactions within a cluster that led to essentially the first detected binary black hole merger. And so you don't have to look at the detail of this picture, but each of these steps in this ladder are an exchange between two bodies or three bodies in this dynamics, in this cluster. And so it's just an illustration to show you that n-body dynamics is complex, has many components, and we're still far away from understanding how all of this works. But we know that in general, in a cluster, the most massive things tend to go to the center. They really sink. So black holes will go to the center. The other thing is that if you have a binary and you have a third body coming in, There will be a few interactions with a triple, and eventually probably the lowest mass object will get kicked out, and the remaining binary will be made of the two most massive objects. So that is really good at making binary black holes or binaries of massive objects, because they tend to stick together. The thing is, in these clusters, you are actually able to make several generations of mergers, because if you have two black holes, they merge, you have a more massive black hole. But if it's still in the cluster, it can interact again with a black hole and make even more massive black holes. And that's one way we actually think that intermediate mass black holes, like 100 or 200 solar mass, could be formed. And clusters are good places to do that. However, binaries can also be kicked of the cluster, really as a binary. So this is your cluster, and my binary ends up here, in which case the merger happens outside of the cluster, and we won't be able to make a new generation because it's completely lost in space. So these are the main ingredients in the dynamics in clusters. It's very complicated to model, and many of these things are also subject to the uncertainties that we know from stellar evolution, because, I mean, stars evolve in the same way in a cluster and in a binary, in the sense that they lose mass and they have supernova explosions. So the uncertainties we have, some of them only matter for binary evolution, some of them matter for cluster evolution, and some of them matter for both. So it's a very complicated picture before we actually reach this population. So I'm going to spend, I guess I have about 20 minutes. I'm going to go a little bit into the detail of what we have observed so far. So this is this picture of the compact object population that we know now. And with LIGO, Virgo, and Kagra, what we measure is the rate of merger. We have some idea of the rate of merger as a function of redshift, going a little back into cosmic history, but not much for the moment. We measure the masses of the objects. We have some idea of the spins, so how they are rotating. And we have some idea of the sky localization and the distance of the sources. That's the information we actually get. And so we have to go from that to understanding stellar astrophysics. So the latest available gravitational wave data is based on the third gravitational wave transient catalog that LIGO and Virgo Kagra published. And in there, we have about 80 binary black holes. And so on the top here, I'm showing the chirp mass of the observed event. So this chirp mass, this beautiful M, is essentially a combination of the two masses of the black holes. And each of these small gray lines is the posterior distribution of the chirp mass of an event. And so posterior distribution is just a fancy word of saying that it translates our uncertainty on the measurement. But basically, each of these lines is one measurement. And you see that we seem to have a lot of mergers around 8, 9 solar mass, and then maybe a gap. And then we have more of them around, we seem to have a pileup of events around 25, 30 solar mass. So this is what we observe. Obviously, our detectors have biases, and more massive objects are easier to detect because they have a stronger amplitude, and so we can see them further out. Also, the LIGO Virgo sensitivity curve is sort of a bucket. And so anything above the sensitivity curve is detectable, but that means that there's a preferred frequency right in the middle of this bucket where things are easier to detect. And that's also corresponds to rather more massive objects. So we have the observed events, and from that we can infer what we think the true population is. Basically reconstruct the mergers that we don't observe. And that obviously means we have to use population models. So this is why this is actually an inferred population. But from the observed population, we have an inferred population. And so we see a mass spectrum that is sort of a power law with more low mass systems than high mass systems, but with quite a few bumps. So with this model, we're able to infer the rate of mergers, which is currently constrained between 17 and 45 events per gigaparsec cube per year. And so this is our 90% confidence interval. I guess you're too young to remember the first papers that came out that had uncertainties that were essentially 100 times larger. And so even with 80 binaries, we've been able to strongly reduce the uncertainty we have. So with this mass spectrum, what we know is that we find a lot of massive black holes. There seems to be this bump around 30 solar mass, and that is actually statistically significant. When we do statistical analysis of this, we know for sure that this bump is real. There used to be a lot of discussion on a potential mass gap between neutron stars and black holes. The idea that between the most massive neutron star and the lowest mass black hole, we shouldn't have any compact objects. And this was an idea that was mostly based on observations in our Milky Way, where we find black holes of about 5 solar mass, but nothing below. It turns out that the analysis from LIGO and Virgo seems to suggest that that mass gap doesn't exist for real. It's not completely certain yet, but that seems to be the case. So we see all these features in the mass spectrum. So the 30 solar mass bump is real. This bump around 8 solar mass is also real, statistically significant, but there also seems to be a bump around 15 solar mass in this spectrum, and that at this point, we don't know if that's real or not. So we're waiting for more data to see if that's real. Actually, before I move on here, there will be a lot of more data because the 4th observing run of LIGO, Virgo, and Kagra is officially starting on the 25th or 26th of this month. And it's going to be for a year and a half. And we expect something like 300 or 400 events. And so we expect that in a year and a half, we will know whether this middle bump is real or not. So most of the black holes we see have 25, 30 solar mass, and that is actually really massive. If you come back to this picture of stars losing a lot of mass through winds, if you have a 50 solar mass star at birth and the chemical composition is the same as the sun, it's really never going to make a 30 solar mass black hole because most of the mass will be lost through winds. And so it's all related to the chemical composition of the star. And so this is a plot that is showing the masses of the first events that were detected, these 2 30 solar mass black holes that really came as a surprise to most people. And it's really this 30 solar mass black hole detections that got people into thinking about how they were formed and sort of revived a lot of the studies on massive stars, and it got me completely hooked in gravitational waves. So this was really a very unexpected discovery. But you see that for these 2 events, so the blue line is a model that is showing the maximum metallicity that we expect to make these black holes, a function of the mass of the black hole. And so you see for these black holes, we expect a metallicity that is only something like 20 or 30% of the metallicity of the sun. And so that means that black holes that LIGO and Virgo see are likely coming from low metallicity environments. So what does that mean and where do we even find that? The thing is that low metallicity stars, we don't really know many of them in our nearby environments, especially for the most massive ones. So it's not a population we study very well, and so gravitational waves can be really interesting here. So where do these black holes come from? This is just a pretty image of the Hubble Ultra Deep Field. I guess I should update it with the JWST Ultra Deep Field. But essentially, you see all kinds of galaxies here. You see blue galaxies, which means that stars were formed quite recently in that galaxy. You see red ones, which means that you don't have any recent stars and all of the stars are old. And then we have galaxies that are too faint to even be seen, that are dwarf galaxies. And so one of the things that is driving my research is to figure out which of these types of galaxies is a good host to make binary black hole mergers. So you have to, one thing to understand here is the cycle of metals, of chemical elements through the cosmos. So massive stars form. So you've seen this picture a few times now. Massive stars make winds. So whatever is produced in the star gets expelled to the surrounding medium. Massive stars also make the supernova. And at that point, really all the heavy elements that are made in the stars are being sent into the interstellar medium. And so the next generation of stars will be made out of much more rich gas and will have a much higher metallicity and will probably make smaller black holes. So the problem is that in general, over the cosmic history, metallicity increases, but it doesn't increase in the same way everywhere. So if you have the Milky Way, which is actually a really standard galaxy, most of the stars in the Milky Way have the metallicity like our sun, but our sun is a very standard star in the Milky Way. Now, however, this is an image from the Apogee survey that was looking at many individual stars, and each point shows the metallicity of the stars. Blue meaning low metallicity and red high metallicity. And you see that there's really a gradient between the lowest metallicity on the outside of the galaxy and the higher metallicity towards the center. And there's actually a factor 10 in terms of metal content between center and the outside. And so that means that even in a galaxy like the Milky Way, there's actually a lot of diversity in terms of metallicity. And so we can't just say that all stars in the Milky Way have solar metallicity. They mostly have, but not exactly. Now, if we look at smaller galaxies, so the Magellanic Clouds, which you're lucky enough to see on a regular basis, the metallicity is about half solar for the Large Magellanic Cloud and a quarter solar for the Small Magellanic Cloud. So this would be a good place to make massive black holes. And then the Milky Way has even smaller satellites that have about 15% the solar metallicity. And then we have these really tiny galaxies that we can barely call galaxies that have about 1,000 stars, and where the metallicity is less than 1%. And it looks like these could be really good places to make massive black holes. And so essentially most of my research is trying to model black hole mergers, but based on star formation that is representative of all the diversity that we see in the universe in terms of evolution over time and different types of galaxies. So that's what I essentially do. I'll have a few more minutes and spins, and then I'll open for questions. If that sound okay, Petra? You can just nod if you don't want to tell me.
Yeah, sounds good.
Okay, great, thanks. So gravitational waves carry information on the spins of the merging objects. So they actually have information on the spin that is a combination of the spin of the two objects. So if you have two objects that have about the same mass, the information is equally representative from the two masses. If you have information that is coming from unequal masses, then it will be strongly biased towards the most massive objects. Spin is hard to measure, but we do measure it a little bit. What we actually measure is, so in this picture here, there's this chi effective arrow, this green arrow, which is actually the projection of the spin of the object onto the spin of the orbit. So it's a tricky measurement. It's hard to disentangle. But we know that spin matter a lot because if you have a binary, the spins of the two objects tend to get aligned, just because mass transfer, tidal interactions, all these things tend to align spins, although supernova can slightly disturb them. And in clusters, we expect random motions to lead to completely random spins at merger. So this is what we expect the two formation channels to have different signatures in terms of spin. So here I'm talking about the orientation of the spin. In general, we really don't know to predict the amplitude of a spin. Basically, how fast is the object rotating? That is actually really hard to predict from stellar evolution. But if we look at the orientation of the spin and its magnitude, so these are again based on the observations we have. So on the left, it's showing the magnitude of the spin. And so each small line here is a single detection. And we see that the measurements we have are consistent with zero spin, but they also allow for moderately spinning objects of 0.2. That's it. And if we look at the and there is a long tail of actually possibly highly spinning objects. Now, if we look at the spin orientation, this theta, this angle, it's quite uniformly distributed. And so it looks like an isotropic spin distribution is slightly preferred. And so this comes from this cluster formation. However, there is an overdensity for aligned spins, which seems to indicate that binary formation is also happening. So a last piece of interesting information is that if we look at the most massive black holes, the spin distribution is rather broad, and it correlates with the mostly unequal mass objects. And unequal mass objects could possibly come from this secondary mergers in clusters, where you make one black hole and then you merge them again. And that is a good way to make unequal masses, because one of the black holes would be a second generation and the other one would be a first generation. In that case, you're expected to have also spin. And so it looks like we're seeing things that could be from that channel. So all of this is quite uncertain, but it's confirming this idea that are at least two formation channels in nature. And people who've done much more careful studies than what I'm just doing here with my hands agree on this, that the two formation channels are likely present in the data, although we don't really know exactly which fraction. So I'm actually going to stop here. I have much more to say, but I feel this has been plenty. I just want to emphasize that gravitational waves are really a new way to understand very fundamental components of our universe. Compact objects, stars, or galaxies, if we talk about supermassive black holes that we will see with Lisa. Right now, we know of kilohertz frequencies, but keep in mind that different frequencies means different timescales, different distances, different types of objects. And so as we will have more detectors at lower frequencies, we will see very different things. The things we measure are the rates, masses, and spins. We still don't really know how binaries get to merge. It's an open problem, and I think it will be for a while. So O4 is starting very soon. With a few hundred more detections, I think we'll do a lot, but it's really just the beginning. And I'll stop here. Thanks.
Awesome. Thank you very much. That was really good. And I think for a lot of us, for some of us with very little astrophysics background, is really good intro as well. I am going to ask the floor if anyone's got questions for Astrid.
I guess 6 or 7 p.m. is hard for questions. Don't be shy.
If no one has questions, I'm going to take advantage of the opportunity. I have a question to ask. If anyone else at the same time can think of other questions. So first one is on your slide 23.
Okay.
I think I wondered in the past, but I didn't do anything about it. If you look at the slightly lower mass black holes, how certain are you that some of them maybe they are definitely not neutron stars?
Very good question. So it's a good question because I was the sort of the team leader for the neutron star black hole detection paper. So and for that paper, we really struggled to make sure that we had a neutron star, because just from the masses, we expect it to be a neutron star because it matches the neutron star masses we see in the Milky Way. But effectively, we can only be certain that a neutron star is present if we have signature that there is matter. And that can come in two ways. Either so matter actually has an imprint on the gravitational waveform we receive. Because just before merger, you won't just have a spherical object anymore, but if there's matter, it will be tidally deformed, and that changes the waveform. The problem is that for that to be detected, you need high signal to noise, and you want more or less equal mass objects, because this effect, essentially, if you have an unequal mass merger, all your signal is dominated by the most massive object. So with the case of the neutron star black hole system, all the waveform was dominated by the black hole, so whatever matter proof we could see from the neutron star was completely hidden. We had absolutely not enough signal to noise to see that effect. But if we had, let's say, 2-3 solar mass objects merging, we could go hunt for these, because in the neutron star mergers, we see these matter effects. That's one thing. We could know that there's a neutron star if we obviously have an electromagnetic signature that is also related to the object being shredded and then forming a protoneutron star that might, or a black hole, when you will have an accretion disk and a jet, gamma ray bursts. And with that electromagnetic signature, you know that matter was present, and we know it's a neutron star. For a black hole, we don't expect this, but it would be absence of proof rather than proof of absence. Really, it's difficult in this mass regime. For the neutron star black hole binary detection, we ended up concluding that it was a neutron star just because we have, based on the statistical models we have, based on observations of neutron stars in the Milky Way, but also people who do studies of equations of state and who can predict a maximal neutron star mass. Otherwise, it would become unstable and collapse into a black hole. We were really confident that the object was lower mass than that. To make, for example, a 3.5 solar mass neutron star is rather impossible from a nuclear physics perspective, with what we know now. I guess if we saw one, people would find ways. But so it's a mass regime where we don't really know. LIGO Virgo had a merger with an object of 2.4 solar mass. We still don't know what that thing was. Yeah. Likely a black hole, but we effectively don't know.
Awesome, thank you. There's a question from Tegan. She said, thanks for the great talk. And what would be the most exciting observation in 04 for your research?
Oh, thanks. This is a good question. So okay, a supernova explosion would be really awesome, but I think we won't get that lucky. It would only be observable with the current detectors if it were actually happening in the Milky Way. So that's unlikely. I think there are two things I'd be very interested in seeing. I think an unequal mass binary with really good enough signal to noise so that we can really be sure it's highly unequal mass, because the problem is that all our detections, we quote 90% confidence intervals, and often within the 90% confidence interval, you can still allow for more or less equal mass binaries. So really being sure that it's unequal with spin, that would be really interesting, because then we can really pinpoint to something that comes from dynamic formation. So I would really like to see that. I would also be very interested, but I think that's not really feasible yet with the next run. But just a vanilla merger, 30 solar mass, but with very good signal to noise and 3, possibly 4 detectors contributing to the detection, which means we can have very good sky localization. Because I think someday we'll be able to have some idea of where these things come from, but we really need exquisite sky localization, and probably not now, but let's give it 10 years, and then I think that would be really interesting. Those are the things that I'm most interested in. I think a lot of people are really looking forward to a new multi-messenger event. So an event with a neutron star where we have an electromagnetic counterpart with a gamma ray burst or a kilonova, maybe something else. A lot of people are really waiting for that. It's not really what I do, but there will be beautiful science if we get something like that. So that's also high up on the list.
Thank you. That's very exciting. Anyone else got any questions? You can put in the chat quickly. I'll count to 3. Tiga says, thanks, finger crossed.
Oh, thanks.
Okay, if there's no one has any question, I have one more question.
Go for it.
It's something someone else just joined our team and looking at triple systems and the MIMB pass. I just wonder about, I have not looked at triple system at all. I don't even know anything about it. And you talked about how in smaller clusters or in globular clusters, you may have the hierarchy of the gravitational events. I just wonder if we detect all these events, they are from binary merger. Will if we detect a triple merger, how is it going to be different from the binary merger?
So many people are doing triples now. It seems to be the new binaries. So the triple, so likely it's going to be a triple with a hierarchy. So you have an inner binary and an outer triple. there's likely going to be a lot of exchanges between the inner and the outer in terms of mass, or just replacing one object to the other. So in terms of population, I think the triples will look differently than the binaries in general. However, we don't expect three things to merge together like this. It's highly unlikely. But there are extreme cases where people expect, for example, that the triple will give a little bit of eccentricity. But whether that's measurable in LIGO Virgo is probably not the case, because at that point you're extremely circular already, but it could be detectable with LISA. So yeah, with LISA, triples can probably be, we can find a signature of a third. But otherwise, I think it's more of a population type thing, where the masses of the object would be slightly different in a triple than in a binary. The time scales of evolution might also be quicker. So I'm not sure of what I'm saying here, but my guess is that if you have a triple, you could evolve faster and maybe get tighter, which means that you might track star formation more closely, not have that much of a delay time. So you might see a signature of that in how the merger rate evolves with time. But yeah, so I think this is something we'll get into in a few years when we have that information. That would be my guess. Also, I'm not an expert on triples, but that's my... Yeah.
Cool. Well, thank you so much for the
thank you.
Awesome talk. And if no more questions, let's thank Astrid again. And yeah, we'll have a good day. And thank you very much.
You too. Have a good evening. And well, I guess see you soon in Nice, Petra.
Yes. See you soon.
Bye, everyone. Have a good evening.
Thank you, guys. And everyone else, we'll see you guys tomorrow, 9 o'clock. Good night, everyone.